Hey guys, how's it going? I'm back at you here with day 5. Great first week of class. I want to continue to see you guys work well in groups, discuss, try, right, struggle with some things. I'm putting some problems in there intentionally that are difficult to help you process and think and adapt to new things. So today's video is about two things: types of discontinuities and limit properties. So let's start with types of discontinuities. We have 3 different types that we're going to look at. First is called removable. I'm gonna talk about these in terms of a picture first, and then going back to our definition of continuity at a point, we'll kind of clean it up after that. So let's start with the first type we have. The first is called removable. Removable discontinuities. So here's what they look like. Here's what pictures look like for removables. We've seen these before. When you see the word removable, think whole. So this is a removable discontinuity. So that graph there has a removable discontinuity at x equals a because the function is undefined at a. This also, here's another picture of a removable discontinuity. So this second picture here also has a hole, but notice it's a hole that's filled in somewhere else, whereas the first graph was a hole that was never filled in, right? So like in the first graph, f of a is undefined. In the second graph, f of a is defined, okay? But it's not the same as the limit as x goes to a. Okay. So both of those are removable discontinuities. Let's take a look at the second type. Okay. The second type is jump discontinuities. And you can probably anticipate what we're going to see on a jump discontinuity. That's one example of a jump discontinuity. Here's another one. By the way, this one up here could be filled in and this one could be open, or they could both be open. Jump is there's a skip up or a skip down. That picture is another example of a jump discontinuity. I should label it A. So those are 2 examples of jump discontinuities. What I want you to think about is it's pretty easy to tell the difference between removable and jump when we're looking at a graph. But if we're talking about functions and limits, what's going to be the difference between a removable discontinuity and a jump discontinuity? The third one we're going to talk about is called an infinite discontinuity. So here we see an infinite discontinuity. Right? So when we think infinite discontinuity, we should be thinking about vertical asymptotes. Okay? So let's go back, and I'm gonna after the words removable, jump, and infinite, I'm gonna add in some stuff in terms of limits, right? So how can we identify these if we don't have a graph? How do we know if something is a removable discontinuity, or a jump discontinuity, or an infinite discontinuity without a picture? So take a look here at removable. Okay? What do you notice in these pictures? Well, if we think about our 3 steps to proving continuity at a point, the first step is the limit must exist. Take a look at these graphs. Do the limits exist in these graphs? The answer is definitely yes, right? Because we look at the right hand and the left hand limits are going to be equal here in both of these cases. So we know a removable discontinuity must pass step 1 in proving continuity at a point. So in a removable discontinuity, the limit as x goes to a of f of x exists. It's going to pass step 1 in our continuity at a point because the limit exists. And it's either going to fail step 2 or step 3. Step 2, the graph on the left fails step 2. And so the limit exists, but f of a is undefined, like in the left graph, or f of a, it is defined, but does not equal the limit. Okay. So if we know a limit exists, but either f of a is undefined or f of a does not equal the limit as x goes to a of f of x, we know we're dealing with a removable discontinuity. That's important. A lot of students can easily tell by the graph, but then I give them a function and they're unsure. Okay. Jump discontinuity. In jump discontinuities, does the limit exist? Well, the answer is no. The right-hand limit and the left-hand limit are different. So if we have a right-hand limit and a left-hand limit that are different, but to distinguish it from infinite, they don't go to plus or minus infinity, right? They go to a number, right? We can say that a jump discontinuity is going to happen when the limit as x goes to a plus does not equal the limit as x goes to a minus. But both of those right-hand and left-hand limits aren't infinite, right? We don't have plus or minus infinity. Neither our right-hand limit nor our left-hand limit are plus or minus infinity. Okay. For an infinite discontinuity, our right-hand and left-hand limits are going to either be plus or minus infinity. So that's how we can tell the difference between those 3 discontinuities there. I just want to quickly do our limit properties really quick. These are properties that can help us to evaluate more complex limits later on. Okay, we're going to put a box around these limit properties. Here's property 1. If we're evaluating the limit as x goes to c or a or whatever letter of f of x plus g of x, we can just split this into the limit as x goes to c f of x plus the limit as x goes to c g of x. So if we ever ask you a compound, like we're doing the limit of function plus function, you can just do the limit of the first plus the limit of the second. Okay. The second one in the book also is if it's subtraction, it still works. So I'm going to condense that into just one rule. I'm going to say plus or minus g of x plus or minus over here. So if we're doing the limit of two functions added or subtracted, we can just do the limit of the first plus or minus the limit of the second. This also works with multiplication as well. 2. Limit x goes to c. I'm doing the limit of f of x minus g of x. I can just split that into the limit as x goes to c f of x times the limit as x goes to c g of x. 3. If I have a constant that I'm multiplying by a function within the limit, I can just throw that out front. So here's what this one looks like. Limit as x goes to c of k, where k is a constant, times f of x. Right? This has to be the same as k times the limit as x goes to c of f of x. Our fourth and last rule is this. It also works with division. This works as long as the limit as x goes to c of g of x, as long as this does not equal 0. It doesn't work when we divide by 0. Okay. So that's it for today. Go ahead and box those in your notes, and have a great weekend. I will see you Monday. Bye.